Welcome! Today, we'll be solving LeetCode problem number 485, max consecutive ones. This problem challenges us to determine the maximum number of consecutive ones in a given binary array. It's a great exercise to improve your understanding of array traversal and basic logic building. Let's dive in. In this problem, we are working with a binary array called nums, which consists only of zeros and ones. Our goal is to determine the maximum number of consecutive ones present in the array. For the input, we are given the binary array nums, which has a length of n. The output will be a single integer that represents the length of the longest sequence of consecutive ones in the array. To better understand the problem, let's look at an example. Suppose the input array is 1, 1, 0, 1, 1, 1. In this case, the output is 3, as the longest sequence of consecutive ones is 1, 1, 1, which has a length of 3. Now, let's explore another example to clarify the problem further. If the input array is 1, 0, 1, 1, 0, 1, the output would be 2. This array contains 3 separate segments of consecutive ones, 1, 1, 1, and 1. Among these, the longest segment is 1, 1, which has a length of 2. In a different scenario, if the input array is 0, 0, 0, 0, the output is 0. Since the array contains number ones at all, there are no consecutive ones, and the result is simply 0. Let's consider the constraints and some edge cases to better understand the problem space. First, the constraints specify that the length of the array, nums, will be at least 1 and at most 100,000. Additionally, every element in the array nums is guaranteed to be either a 0 or a 1. Now, for edge cases, if the array consists entirely of ones, such as 1, 1, 1, 1, then the output should equal the length of the array, since the entire array forms one continuous segment of ones. On the other hand, if the array contains only zeros, such as 0, 0, 0, 0, the output would be 0, as there are number ones to form a sequence. Additionally, if the array has just one element, the result depends on whether the element is a 1 or a 0. For example, if the array is 1, the output would be 1, as the single element itself forms a segment of length 1. But if the array is 0, the output would be 0, as there are number ones. Finally, for an alternating sequence like 1, 0, 1, 0, 1, the maximum number of consecutive ones is just 1, as each segment of ones consists of a single element. These examples and edge cases help us understand how the problem handles varying input scenarios and prepares us to consider multiple approaches for solving it. To solve LeetCode problem number 485, the goal is to find the maximum number of consecutive ones in a binary array. One of the approaches we considered was the brute force method. The intuition behind this method is straightforward. We iterate through all possible subarrays of the input array, count the number of consecutive ones in each subarray, and keep track of the maximum count. This can be implemented using 2 nested loops, one to fix the starting index of the subarray, and the other to iterate through the following elements until we encounter a 0. While this method works, its time complexity is n squared, which makes it inefficient for large inputs. Additionally, it uses constant space since no extra data structures are required. However, the major drawback of this approach is its quadratic complexity, which leads to poor performance as the size of the array increases. Now, a more efficient solution is the optimized single-pass approach. This method allows us to traverse the array just once while maintaining a running count of consecutive ones. The key idea is to use 2 variables, max_count to store the maximum number of consecutive ones observed so far, and current_count to track the current streak of ones. As we iterate through the array, if the current element is 1, we simply increment current_count. If we encounter a 0, we update max_count if current_count is greater, and then reset current_count to 0. At the end of the traversal, we ensure that max_count reflects the longest streak, even if the array ends with ones. This approach is highly efficient, with a time complexity of n, since it processes each element exactly once, and a space complexity of 1, as no additional data structures are used. It's also simple to implement and ideal for large arrays. An alternative method we explored is the sliding window approach. Although sliding windows are often used for problems involving variable length subarrays, it can also be applied here to track the length of consecutive ones. With this method, the window dynamically expands as we encounter ones and resets when we hit a 0. However, upon closer examination, this approach is essentially identical to the optimized single-pass solution, with the added abstraction of thinking in terms of windows. This makes it redundant and unnecessarily complicated for this specific problem. The complexity remains O(n) for time and O(1) for space, but it doesn't provide any additional benefits over the single-pass approach. For this reason, the sliding window method is not the most practical choice here. Ultimately, the simplicity and directness of the optimized single-pass approach make it more suitable. The key insight for this problem lies in recognizing that consecutive ones can be efficiently tracked using a simple counter that resets when a 0 is encountered. There's no need to explicitly form subarrays or maintain any additional state beyond the current streak, which eliminates the redundant work performed in brute force methods. When comparing approaches, the brute force method, while easy to understand, is far too slow due to its O(n)² time complexity. On the other hand, the optimized single-pass approach strikes the perfect balance between simplicity, efficiency, and clarity, achieving an O(n) time complexity with constant space usage. The sliding window approach, though feasible, adds unnecessary abstraction without improving efficiency. These trade-offs make the optimized single-pass approach the clear winner, offering the most effective and elegant solution to this problem. This problem focuses on finding the longest streak of consecutive ones in a binary array, where the array contains only zeros and ones. Our goal is to efficiently compute the maximum number of consecutive ones. To achieve this, we use a sliding window approach. The algorithm begins with two key variables, max_count to track the maximum streak of ones encountered so far, and current_count to track the length of the current streak of ones. Both are initialized to 0. Then, we iterate through the array to evaluate each element. If the element is 1, it contributes to the current streak, and we increment current_count. This way, we build the foundation for dynamically tracking streaks of consecutive ones while traversing the array. If the current element is 1, we update max_count to ensure it always reflects the larger value between the ongoing streak and the longest streak observed so far. However, if a 0 is encountered, the streak is broken, and we reset current_count to 0. This ensures that the counter only tracks consecutive ones. To handle edge cases, we verify whether the array is empty. If it is, we return 0 since number ones are present. Arrays consisting entirely of zeros or ones are handled naturally by the algorithm, as max_count is updated dynamically during traversal. Finally, once the loop ends, max_count contains the result, representing the maximum number of consecutive ones in the array. The sliding window approach ensures that we dynamically track and reset streaks as needed, processing the array in a single pass for optimal efficiency. The algorithm is highly space efficient, requiring only two variables, max_count and current_count, resulting in a constant space complexity of O(1). The input is a single integer array, so no additional data structures are necessary. From a complexity perspective, the algorithm processes each array element exactly once, resulting in a time complexity of O(n), where n is the array's length. Now let's examine a practical example with nums equals 1, 1, 0, 1, 1, 1, starting with max_count equals 0 and current_count equals 0. For the first element, which is 1, current_count increases to 1, and max_count is updated to 1 since it's the maximum of 0 and 1. For the second element, another 1, current_count becomes 2, and max_count is updated to 2, reflecting the ongoing streak of ones. As we continue, the third element is 0, which breaks the streak, so we reset current_count to 0. The fourth element is 1, restarting the streak, so current_count increases to 1, but max_count remains 2 as it's already the longest streak so far. The fifth element is another 1, increasing current_count to 2, and max_count remains unchanged at 2. Finally, the sixth element is a 1, extending the streak to 3. At this point, max_count is updated to 3, which is now the longest streak. By the end of the loop, the result is max_count equals 3. This example demonstrates how the algorithm dynamically tracks and updates the streaks of ones. The Python implementation of this algorithm starts with defining a function that initializes max_count and current_count to 0, then iterates through the array to apply the described logic. The implementation continues by checking each element in the array. If the element is 1, current_count is increment, and max_count is updated to the greater value between the two. If the element is 0, current_count is reset to 0 to break the streak. At the end of the loop, the function returns max_count as the result. For edge cases, such as an empty array, the function returns 0 since there are no elements. If the array contains only zeros, the result is also 0 because there are number ones to form a streak. For arrays with all ones, the result is the array's length, as the entire array is one long streak. Lastly, alternating patterns like 1, 0, 1, 0, 1 result in the longest streak being 1, as no consecutive ones exist. These examples highlight the robustness of the algorithm across various scenarios. The provided solution efficiently calculates the maximum number of consecutive ones in a binary list by iterating through the elements using a single loop. Let's break it down step by step. 1. Initialization. Two variables are initialized. Max_count keeps track of the highest number of consecutive ones encountered during traversal. Current_count tracks the count of the current streak of consecutive ones. 2. Iteration. The loop iterates through each element of the input list nums. If the element is 1, it increments the current_count by 1, representing an ongoing streak of consecutive ones. After updating current_count, it compares this value with max_count and updates max_count if the current streak is the longest seen so far. If the element is 0, the streak ends, and current_count is reset to 0. 3. Result. After the loop completes, max_count contains the length of the longest streak of consecutive ones in the array, which is returned as the result. ### complexity analysis. Time complexity, O(n), where n is the length of the input list. The algorithm makes a single pass through the array. Space complexity, O(1), as no additional space is used beyond the two counters. ### edge cases. If the input list is empty, the function will return 0 since there are number ones. If the list contains only zeros, the output will also be 0. If the list contains only ones, the output will equal the length of the list. This solution is optimal for the problem constraints and ensures clear and efficient handling of all possible input cases. This is the Java implementation of LeetCode problem number 485, max consecutive ones, using the same logic as the provided Python solution. The method iterates through the array, using variables to track the current streak of consecutive ones and the maximum streak found so far. Key differences from Python include explicit type declarations for variables and the use of Java's math.max function for comparison. The implementation is concise and adheres to standard Java conventions. To solve this problem, we start by looking at the input array nums equals 1, 1, 0, 1, 1, 1. The goal is to find the maximum number of consecutive ones in this array. First, we initialize two variables. Max_count is set to 0 to track the highest count of consecutive ones found so far, and current_count is also set to 0 to keep track of the current streak of ones. We then iterate through each element in the array. For the first element, which is 1, we increment current_count to 1 and update max_count to the maximum of 0 and 1, which results in max_count equals 1. On the second element, also a 1, we increment current_count to 2 and update max_count to the maximum of 1 and 2, giving max_count equals 2. However, when we reach the third element, which is 0, the streak of consecutive ones is broken, so current_count is reset to 0. Moving forward, the fourth element is 1, so we increment current_count to 1 again, but max_count remains unchanged at 2 since the current streak is smaller. For the fifth element, which is another 1, current_count increases to 2, and max_count is still 2. Finally, we process the sixth element, another 1, and see what happens next. For the sixth element, which is 1, we increment current_count to 3. At this point, we update max_count to the maximum of 2 and 3, which results in max_count equals 3. After iterating through the entire array, we return max_count, which is 3, as the final result. This means the longest streak of consecutive ones in the input array is 3. To summarize the intermediate states, at index 0, current underscore count is 1 and max underscore count is 1. At index 1, current underscore count becomes 2 and max underscore count updates to 2. At index 2, the streak is broken, so current underscore count resets to 0 while max underscore count remains 2. At index 3, the streak starts again with current underscore count at 1, and at index 4, it increases to 2. Finally, at index 5, the streak reaches its peak with current underscore count at 3, and max underscore count is updated to reflect this. The final output is 3. Now, let's look at another example with the input array nums equals 1, 0, 1, 1, 0, 1. As before, we initialize max underscore count and current underscore count to 0. For the first element, which is 1, we increment current underscore count to 1 and update max underscore count to the maximum of 0 and 1, resulting in max underscore count equals 1. The second element is 0, which breaks the streak of ones, so we reset current underscore count to 0. When we encounter the third element, which is 1, we increment current underscore count to 1, but max underscore count remains 1 since the current streak hasn't exceeded the maximum so far. On the fourth element, also a 1, we increment current underscore count to 2 and update max underscore count to the maximum of 1 and 2, giving max underscore count equals 2. For the fifth element, a 0, the streak is broken again, so current underscore count resets to 0. Lastly, we process the sixth element, another 1, and analyze the result. On the sixth element, which is 1, we increment current underscore count to 1. However, max underscore count remains 2 since the current streak of ones does not exceed the longest streak found so far. After iterating through the entire array, we return max underscore count, which is 2. This indicates that the longest streak of consecutive ones in this input array is 2. To summarize the intermediate states, at index 0, current underscore count is 1 and max underscore count is 1. At index 1, the streak is broken, so current underscore count resets to 0 while max underscore count remains 1. At index 2, current underscore count is 1 again, and at index 3, it increases to 2, updating max underscore count to 2. At index 4, the streak is broken once more with current underscore count back to 0, and at index 5, current underscore count rises to 1 again, but max underscore count stays at 2. The final output here is 2. In this final example, we examine the input array nums equals 0, 0, 0, 0. Starting again with max underscore count equals 0 and current underscore count equals 0, we iterate through the array. The first element is 0, so we reset current underscore count to 0. The second element is also 0, and again, current underscore count remains at 0. Similarly, for the third and fourth elements, which are both 0, current underscore count stays at 0 throughout. Since there are number ones in the array, there is no streak of consecutive ones to count. As a result, we return max underscore count equals 0 as the final result. Looking at the intermediate states for this example, at every index from 0 to 3, the value of number is 0, which keeps current underscore count at 0 and max underscore count at 0. There is no streak of ones, so the longest streak is 0. The final output for this input is 0, which confirms that the solution correctly handles cases where the array contains number ones at all. The time complexity of our algorithm is O(n), where n represents the length of the input list, nums. This is because we use a single for loop that iterates through the entire list exactly once. Each iteration of the loop involves constant time operations, such as checking if the current element equals 1, incrementing or resetting the current streak counter, and updating the maximum streak. These operations all run in O(1) time. Since the loop executes n times and each iteration is O(1), the overall time complexity is O(n). Importantly, this holds true for the best, average, and worst cases because the algorithm always processes every element in the list, regardless of the arrangement of ones and zeros. Now let's discuss the space complexity, which is O(1). This is because the algorithm uses only two integer variables, max underscore count and current underscore count, to track the maximum streak of consecutive ones and the current streak, respectively. These variables require a fixed amount of memory, regardless of the size of the input list, nums. Since no additional data structures are utilized and the algorithm does not involve recursion, the space usage remains constant. This makes the solution extremely space efficient. To put this into perspective, let's compare the optimal approach with a brute force solution. A naive method would involve iterating through every possible subarray of the input list to count consecutive ones. This would require two nested loops, the outer loop to determine the starting index of each subarray and the inner loop to count ones within that subarray. Consequently, the time complexity of such an approach would be O(n squared, which is significantly less efficient than our O(n) solution. Additionally, brute force might require extra memory to store intermediate results, leading to higher space complexity. In contrast, our optimal approach uses a single pass through the list and only two integer variables, achieving O(n) time complexity and O(1) space complexity. Let's solidify our understanding with a mathematical proof. The input list, nums, has a size of n. The algorithm consists of a single for loop that iterates n times. Within each iteration, constant time operations such as condition checks and variable updates are performed. This gives us O(n) iterations multiplied by O(1) operations per iteration, resulting in a total time complexity of O(n). As for space complexity, we only use two integer variables throughout, which requires constant memory. Therefore, the space complexity is O(1). In summary, this solution is optimal, with a time complexity of O(n) and a space complexity of O(1), making it far more efficient than a brute force approach in both time and space usage. When solving the max consecutive ones problem, there are a few common mistakes to watch out for. First, not resetting the count when a zero is encountered can lead to incorrect results. This happens because the count would continue to accumulate, even across non-consecutive ones, which defeats the purpose of the problem. Another common pitfall is misinterpreting edge cases, like an empty array or an array that contains only zeros. If these scenarios aren't handled properly, your solution might crash due to accessing out-of-bound indices or return incorrect values, such as a non-zero result for an array with number ones at all. Finally, initializing variables incorrectly, such as setting max_count to -1 instead of 0, can also cause errors. This is especially problematic when the array has number ones, as it would lead to a negative result, which makes no sense in this context. Now, let's consider inefficiencies and overcomplications that can arise. Using nested loops to calculate the length of consecutive ones at every index is a common brute force approach, but it's highly inefficient. This results in an O(n squared) time complexity, which is unnecessary for a problem that can be solved in linear time. Similarly, overcomplicating the solution by introducing additional data structures, like stacks or extra arrays to track counts, adds unnecessary space complexity. For example, using an auxiliary array to store intermediate results might increase the space usage to O(n), when the problem can easily be solved with O(1) space. Both of these mistakes make your solution less optimal and harder to explain in an interview setting. This problem is a great example of how recognizing common patterns is key to solving it effectively. The ability to identify this as a sliding window or counting problem is crucial. Maintaining a running count and resetting it when a zero is encountered is the essence of the solution. During an interview, it's also important to address edge cases up front. For instance, clarify what the output should be for an empty array or arrays with number ones at all. Highlighting the efficiency of your O(n) solution and contrasting it with a brute force approach can really make your answer stand out. Additionally, be prepared for follow-up questions, such as extensions of the problem. For example, if you're allowed to flip one 0 to a 1, how would you adapt your solution? Or, if the array is streamed and you cannot store all elements in memory, how would you handle that scenario? These are common variations that test your ability to generalize and optimize your approach. This problem also connects to several related problems that you might encounter. For example, LeetCode number 487 asks you to modify at most one 0 to a 1 and return the maximum number of consecutive ones. Another variation, LeetCode number 1004, allows you to flip up to k zeros to ones. Both of these problems build on the same foundational logic but add an additional layer of complexity. Moving beyond binary arrays, LeetCode number 674 focuses on finding the longest continuous increasing subsequence in any array, which involves a similar strategy of maintaining a running count. Finally, while seemingly unrelated, LeetCode number 1041, robot bounded in circle, is another problem that emphasizes pattern recognition in sequences. These connections highlight how mastering this problem can set the stage for tackling a wide range of related challenges. There are multiple approaches to solving the max consecutive ones problem, each with its own trade-offs. A brute force approach involves iterating over all possible subarrays and calculating the length of consecutive ones for each one. While this is simple to understand, it's highly inefficient, with a time complexity of n squared. On the other hand, the two-pointer or sliding window technique is much more optimal. By using two pointers to traverse the array and resetting the count whenever a zero is encountered, this approach achieves n time complexity with 1 space. For scenarios where the data is streamed or too large to fit in memory, a streaming processing approach can be used. Here, you calculate the current and maximum counts on the fly without storing the entire array. While this is memory efficient, it can be harder for beginners to implement. Each approach has its use case, but understanding the trade-offs is essential to choosing the best method for a given situation. Great job! To summarize, we solved the max consecutive ones problem using an efficient traversal approach with n time complexity. This type of problem helps improve your array manipulation skills and is great practice for interviews. Thank you for watching, and don't forget to like, subscribe, and stay connected for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!